Hello and good evening, everyone, to our second session in the Clinical Research and Publication Pearls. This webinar series we're bringing you through VPS Healthcare, endorsed by the American Oncology Society. My name is Dr. Khaled Musallam. I'm the Group Chief Research Officer at VPS Healthcare in Burjeel Medical City. I'm also an adjunct professor at Khalifa University and president of the International Network of Hematology. For those of you that weren't with us in the first session, so this is a series of webinars that are dedicated, as the name implies, to clinical research and manuscript writing for a target audience of physicians and scholars such as yourself, where we're trying to, in such short sessions, cover more or less the basic elements that you would be facing in your clinical research journey, in your academic journey, trying to touch upon the key aspects of research from idea generation to analysis to putting together a manuscript as much as we can in terms of coverage. And this is mainly the whole course is stemming from my personal experience. I've been through this. I've been through the ups and downs of research and publications. So you will see that a lot of the training, I would say, is not theoretical, but rather more practical. So it just touches upon the things that you need to know. While obviously, if you require further reading, you can always go and do that through typical resources. I will say this at the end as well for those who aren't with us in the beginning, that we will make those slides and the recording available through the US website at the end. So we basically have 4 sessions. We already covered one last Wednesday on study design essentials, everything from observational studies to clinical trials. What do different study designs mean in the research context? Today, we're going to go a little bit more in depth into statistical analysis and how you can match the research questions that you have at hand that you designed a study for with specific statistical tests. Next week, we will also go into more of the interpretation of the results. So as much as you understand statistics and get your data out, but what does that data actually mean? How do you interpret the results? And the last session, we combined it just for the sake of the timing of having two, will end up being in Ramadan. So it will be a bit of a longer session covering everything in publication planning and journal selection into putting together your data into a manuscript for a medical journal. So this would be almost 1 hour session today. I warn you, it's a bit, it could be a little bit intense. I try to avoid mathematics as much as I can but it's sometimes hard to talk about statistics without going into mathematics a bit, just for you to understand the concepts of things. This session is not intended in no way to make you a statistician. Our colleagues that as statisticians have, over 4 years of education to become actually labeled as biostatisticians. This is more to give you a sense of terminology, things that you need to be aware of when you read papers. When someone mentions a test, what does it mean? What is it trying to achieve? And also for you to speak to statisticians, but obviously for some simple analysis that might allow you to do the analysis yourself. We can, if it is on demand, also maybe after we finish these more theoretical and practical webinars, design more of a hands-on training on use of SPSS, for example. So all the analysis methods that I will cover today, we can look at them together and see how we can actually go over these and try to mimic what you would do in a research study for a publication. Okay, I always like to start this part with few quotes, and I'll actually read them out loud. They're there on the screen, obviously, but I feel they link a lot to what I'm going to be saying in the next few slides. So the first one is, if you can't convince them, confuse them. And that's something that's very true about statistics. Sometimes it's confusing. And to be honest, I've found it unfortunate that sometimes when people get confused with statistics, they just move forward with the information without actually even trying to understand what is it that you're looking at. I've seen that actually happen sometimes from reviewers, even in medical journals. If you send them just a batch of complex statistics, you see much less comments to your paper, just simply because you probably that the statistics were not as easy or as clear. The second is saying, as far as the laws of mathematics refer to reality, they are not certain, and as far as they are certain, they do not refer to reality, and that's by Albert Einstein. And you'll see how much the concept of uncertainty in statistics matters, and we will cover that actually a little bit more in the second session next Wednesday, where we talk about confidence intervals and all these aspects that relate more to the certainty and estimation of findings rather than the exact science that people think statistics would give. And then be suspicious of anything that works perfectly. It's probably because two errors are canceling each other out, and that's usually true. And don't put your faith in what statistics say until you have carefully considered what they do not say. And that's probably is one of the most important quotes to me, because it's always about not getting too excited about a finding until you understand what it means on the other way around. And we will make a lot of those examples and comparisons later on. An approximate answer to the right question is worth a great deal more than a precise answer to the wrong question. And we'll talk about precision in statistics in this course and in next week. If you torture the data long enough, it will confess. Obviously, that was referring to something else. But that is kind of true. That is sometimes true. As much as you're not able to do that in terms of intent, usually whenever, as we mentioned in the last presentation, when you design a study, especially a trial, you have to actually already mention what is it that you intended to find in it, and you have to stick to that. But there's always that chance to look into your data again and again and do some data mining and try to tease out things, and you might find actually things that you didn't even originally observe or intend to look into. The first and probably one of the most important parts of statistical analysis or data analysis is dealing with your data to begin with. So you need to obviously first collect your data, whatever the study was, whether it's observational or clinical trial. You need to go to the charts, get your clinical information, to the lab reports, to the imaging reports, whatever the data source is, interviews of patients, and these form the data source that you would need to probably enter to take it from the source file, as we call them, into some sort of electronic database. That could be something that is very simplistic as Excel on Microsoft. Obviously, Excel is not that simplistic, but compared to statistical software. And then you do some data migration. So the data is probably maybe easier prepared and filed in some sort of Microsoft or certain databases design. But then when you need to do analysis, you need to move all this data to the statistical software. I personally prefer to already collect my information in the statistical software so I can avoid this data migration process, which might cause some errors or some issues if the information is actually not transferred correctly. Data cleaning is probably the most important part, because that's where you start discovering errors, abnormal values, missing values. You do some queries if you're doing a multi-center study and you have your data and your collected blood pressure, and then you see blood pressure recorded as 20. That's where you spot it there, and you go back to the site to actually be able to correct it because it was maybe 120, but it was recorded wrong in the report. And then data management is the last step before you go into your analysis, because the data, as we retrieve them and record them and have them in terms of our databases or statistical programs, aren't usually almost immediately ready for analysis. We still need to do some calculation, some categorization, some recoding, which I'll touch upon in a bit when I'm talking about variables per se. But often, you would have a database that you collected height and weight in, but you still need to work on BMI, for example. So you still need to manage this data and calculate your BMI from the weight and height, and then that BMI becomes your new variable for the analysis. So speaking of variables, we have different types of variables, but these are the data points that you collected from your study, from the source charts, from the source labs, from the source reports, that you are doing your analysis on. They are the basis of everything you're going to do in this study. And the main two big umbrellas of variables, probably there are more, but just for the sake of simplicity for this course, we mainly speak of continuous and categorical variables. And as the name implies, a continuous variable is usually numeric, something that you can put in a number line. That could be age, height, weight, hemoglobin level, blood pressure. It's something that can be calculated also, like BMI. So it doesn't need to be already something you measure, but you can actually calculate it from various variables that you measure. As much as it is continuous, you can still categorize it if you want. So age is a continuous variable. You can put it in a number line. It spans, obviously, we can't have a negative age. It's from 0 up until 100 something. But you can still categorize age and split your patients, for example, around the age of 65 years, less than 65 and more than 65. So you can convert a continuous categorical variable. So what is a categorical variable? Again, as the name implies, it's a variable that can be divided into categories, or it is divided into categories. Mind you, it can still be numeric. And that is something that many people get confused with. For example, if we look at the ECOG performance status criteria in oncology, for example, where it gives a score of 0, 1, 2, 3, 4 to patients based on their performance status, just because they are numbers, those categories of performance, doesn't mean that this is a continuous variable. These are still categories. They just happen to be labeled as 0, 1, 2, 3. Obviously, gender, death status, yes, no, anything that can be grouped into more than one group is a categorical variable. And we usually subdivide those into nominal, where there is no relationship between those variables in terms of order. So like gender, you have male and female. But we can also have ordinal variables, like the example that I just gave, the performance status, the ECOG performance status, for example. This could be 0, 1, 2, 3, 4. So these are, let's say, 4 categories. But we know that they have an order to them. So the higher the group, the more severe the disease, for example. When we put things in a statistical software or a statistical program, they do not see to perform analysis, you need to deal with numbers. You cannot deal with letters. You cannot deal with text. Obviously, you can always list text in those software, but when you need to do analysis, you need to convert all your variables into numbers. For example, if you have male, female listed, you have to convert those into a 0 and 1, for example. If you have death as yes, no, it can need to be converted to 1, 0. Sometimes ordinal variables that are there on a line, on a sequence, sometimes we do treat them, as much as they're not continuous variables, but we do treat them as continuous variables in some analysis, and I'll refer to that in a bit. So what types of analysis do we usually have? We have univariate analysis, we have bivariate analysis, we have multivariate analysis, and again, as the name implies, univariate analysis is any analysis that you would do that deals only with one data variable, so a single variable, for example, something to describe your sample with, patient characteristics, height, weight, age. Bivariate is when you put two variables into the mixture, and then you can link those together through associations or correlations between those two data variables. I will focus on when do we say the word association or when do we say the word correlation later on. Obviously, many people don't even give attention to that. They just use them interchangeably. But if you want to be very exact and a perfectionist in statistics, you need to actually use them in different scenarios. Multivariate, again, is when you have 3 or more data variables and you're trying to see links between them. Usually you have the main link between two variables, and then you're trying to see how a third variable will actually affect this relationship between two variables. And this, we will talk about it in a bit. So the main univariate analysis that you would need to be aware of are the ones that we do typically in the description part of the study at the beginning, the first tables, the first paragraph. And these are different for continuous and categorical variables. When we look at categorical variables, so gender, male, female, death status, yes, no, as an outcome, for example, we usually look at the number of events or number of persons or patients and the percentage. So if I have a study made of 100 patients and I have 40 males, then I have 40 males that give me a percentage of 40%. So it's number and percent. And usually when we want to represent those in figures, that's done by a bar chart or a pie chart, which I'm sure you're all familiar with. When it comes to continuous variables, that's where we say we cannot describe them in this way. So if we have an age spectrum in a study, we usually describe that in a univariate way, in a descriptive way, through what we call a central tendency and a dispersion. So we try to get to a number that represents the central element of this whole group with how, and another number that can give us how wide all the other numbers are from this one. So if I have 100 patients and I have the age for all of these 100, I will need to find an age that I can say comfortably that this represents my group. So it's an age somewhere in this 100 patients' ages sitting somewhere. And also another measure to give a reflection to the reader of how far away my other patients are from this number. There are two types of data when we speak of data. There is what we call normally distributed data and not normally distributed data. I will not go into that into detail, but I'm sure you've got exposed to this at some point during school, during university. And usually we always refer to this bell shape, that if a normally distributed data, you will have all the data coming around a bell shape where everything is maybe piled up in the middle, and then you have all your data is getting less and less in terms of number when you go away from this central line. There are ways to understand if your data is normally or not normally distributed. There are many tests that you can do in these statistical softwares to look at skewness, kurtosis, and some Shapiro, a lot of tests to look into that. But what matters here is that what do you do then after you understand? If your data is normally distributed, you need to describe it with a mean. And then next to the mean, you look into the standard deviation. So the mean is your central tendency, and the dispersion is the standard deviation. Sometimes you would look into standard error. I will go into those more when we talk about confidence intervals later. And you put the range of your data. So if I have a data of 100 individuals with different ages, the mean age would be 64. Usually you put the sign plus or minus. The standard deviation would be 7. Or if it's a standard error, usually it's a smaller number. And then I will put the lowest and the highest range. So the lowest age was 18 maybe, and the highest was 85. When you look at central tendency and dispersion in a non-normally distributed data, so if we know our data is not normally distributed, we will go for a median. And with the median, sometimes we just report the range because we don't have something as similar to a standard deviation. And with the median, you report the range, which is the minimum and maximum value. But if you want to be a little bit more sharp, you need to report something called the interquartile range, which is your 25th and 75th percentile. I'm not going to go into the details of what the mean and median is beyond that in terms of mathematics, because I'm sure you've all been exposed to that. Again, as I said, the purpose of this webinar is for you to connect a certain terminology or a certain mean or a median to a certain analysis or a certain type of variable, because that's what matters. Because at the end of the day, being completely transparent, you can always go to the statistical software and ask for the mean. You don't need to know how it's calculated or what it means like we used to do in school. And I'm sure most of you know how to calculate a mean or a median if you have a data of 20 patients. But obviously, if you have a trial of 1,000 patients, you're not going to do that manually. One thing that I always, because we don't always have that capacity to look into the data to see if it's normally or not normally distributed. Some people just don't know how to do that. There's actually a lot of aspects to that. It's not sometimes just plotting it or looking into a statistician to do that for you. Usually it's done very much in behavioral sciences. But in our studies, when we're doing studies on 30, 40, 50 patients, no one, to be honest, goes into that trouble of understanding the distribution of the data and then selecting analysis accordingly. We use sometimes very simple rules. They're not 100% accurate, but they work. I've used them many times. Is that when a sample size is very small, so it's less than 30, better just go for a consideration that this data will not be normally distributed. So I would report the median and a range with the IQR. And you will even find that if you try to report a mean for a study on 16 patients, you will find that the mean and standard deviation, the standard deviation is very, very high. So it's looking like the data is all over the place and very widely dispersed. So that's why I always prefer when it's less than 30, just as a rule of thumb, just use medians and IQRs. No one is going to challenge you for that. Obviously, you can always report both in the paper, but sometimes it becomes too much. Also, again, if the standard deviation is very close to the mean, that tells you in that sense of it's small and it's very close to the mean, it tells you that the data is more likely normally distributed. When we move to bivariate correlations, we have plenty. And again, I don't expect you to just memorize those, but definitely just to present them to you, and you can always go back to these slides to help you pick the right test for the right research questions. So again, remember that we had continuous variables, categorical variables. And when we say bivariate, we want to find the relationship between two variables. So these tables that I'm going to present next tell you which variable actually, which statistical test to choose to compare two variables, and what does it mean when you deal with it. When you want to compare two continuous variables, for example, the example I give here, age and hemoglobin level, we use Pearson's correlation if we're talking about a normally distributed data. So you did the test and you found out that it's normally distributed, or you went with my simple rule of looking at a sample size of 30, or you do Spearman's correlation for non-parametric data. And what does this test give you? It gives you two values. One is the R and one is the p-value. This R is a value between 0 to 1. And all I want you to know about it now is that whenever you see a report of a correlation, so how is age and hemoglobin correlate in your data, the R is giving you first the direction of correlation. So if the R value is positive, it means as age goes up, hemoglobin level goes higher. If it's negative, it means as age goes up, hemoglobin level goes lower. So there's an inverse relationship, or the opposite, hemoglobin goes up, age goes lower. So they go against each other. And the acceptable interpretation of the R in terms of value, because we said it's from 0 to 1, because it's sometimes very, or mistakenly, people try to look at correlations only by the relevance of a p-value. So this test gives you a p-value. And if obviously if it's less than 0.05, it means it's statistically significant. We will talk about p-values in the third session next week, but I'm sure most of you are familiar at least with the concept. So we immediately say, oh, there is a p-value, it's significant. It means there is a strong correlation. That is actually not true. It means there is a statistically significant correlation, and that's a measure of the sample size, to be honest, and this is what we will learn next week. But what matters more is the R value, this R between 0 to 1. And I put here a list of a very subjective way of looking at this. If you want to just have a very simple rule, if you find that the R is above 0.7, it means there is actually a strong correlation between these two, let's say, variables, age and hemoglobin level. If it's actually lower than 7, it means it's okay, it's good. If it's lower than 0.3, for example, it means it's weak. But you can always refer to these numbers that will tell you what language you can say, because you can say we had a strong statistically significant correlation, or a weak but statistically significant correlation between age and hemoglobin. And what does that mean in terms of strength? This is when you plot these on a line on an XY axis. Obviously, the closest you are to a midline, that's your perfect correlation. That means that you're very sure every time a hemoglobin goes up, age goes up by almost the same magnitude of numeric magnitude. But when you start, you have your line tilting to the right or to the left, it means that it might be that I need to raise age by 10 for hemoglobin to only go by 1. It's not like if I increase the age by 10, the hemoglobin will go by 10. When it comes to continuous versus categorical variables, so if you imagine two categories and you want to compare a continuous variable between them. So if we take the example of those two categories, for example, being two genders, male, you have in your patient group in that study, males and females, okay, and you want to compare the age between males and females. If you're, again, I'm going to always give you the alternate, the test for normally distributed and non-normally distributed. So the parametric, we call them, and non-parametric tests. So if the data is normally distributed, it means I can compare the age in group A versus group B, or the age in men versus women through the independent samples t-test. If it's non-normally distributed, we call it the Mann-Whitney test. So in the first case, it's actually comparing the mean. So the mean age in group A was 27 plus or minus 5 compared to 20 plus or minus 3 in group B. I'm comparing two means, and then you do the independent samples t-test, it gives you a p-value. It tells you if this difference in the means is actually significant. If you're looking at non-parametric tests, non-normally distributed data, a small sample of 16 patients, then I am comparing age in group A, which is maybe made of 10 people, compared to age in group B, and then I will comparing here median. So the median age was 7 compared to 5. The Mann-Whitney U test p-value is 0.001. It means this is significant. Now, in the same analogy, if we just have more than one group, so you have two groups, group A, group B, group C, and you're comparing the mean in the three of them, that's when we use the ANOVA test. And if the alternate to that, if you're doing non-parametric, if you're doing a non-normally distributed data, it's called the Kruskal-Wallis test. Again, it tells you if there is a statistically significant difference between the means of these three groups, or in the case of the Kruskal test, between the medians of these three groups. The last bit of comparison of a continuous variable in categorical groups is the paired sample t-test. And as the name implies, here we're comparing two groups, but it's actually not two groups, it's the same group, but we're looking at it as if it's two groups because we're looking at 2 points in time. For example, I look at the blood pressure of group A at time 0, and then I measure it again, blood pressure of group A, the same group, at time 2. So we're as if virtually considering them two groups and comparing the last reading compared to the first reading, and it gives you a p-value, the paired sample t-test. If you're comparing means, same thing. The non-parametric is to go to the Cochrane's or Wilkinson test for the non-parametric or non-normally distributed. And the last analogy for those is the comparing categorical, and the famous one is the chi-square test, which is looking at, for example, what is the percentage of males versus in group A versus the percentage of males in group B, or percentage of certain, let's say, characteristic of a patient in group A versus group B. So you're having your typical 2x2 table. That's where you use the chi-square test, and you report n%. So we say there was 33% males in group A versus 27%. The P was 0.6. It's not statistically significant. That's the chi-square test, where again, it's non-parametric data. You can use the Fisher's exact test, not in the sense of non-parametric in the distribution, but let's say that rule of less than 30. And again, similar to what we did before, if you have more than one, if you have the same group, but you're comparing them in 2 points of time, so you're dealing with it as if it's two groups, but it's actually the same, just different times. So what was the percentage of patients with high blood pressure in time 1 versus after 3 months? And that's where you compare those two percentages using the McNemer test. It will give you the p-value that you need. This next list of let's say metrics that or measures in statistics are very key because they determine a lot of things that we will talk about later and next time. And I will explain them here and then give you an example of how we calculate them so that they make a little bit more sense. We have something called prevalence, which is the number with outcome among group in specific time point or period. And this is what we usually report in cross-sectional and case-controlled studies. If you actually were with us last time, the odds is the number of individuals with the outcome versus those without the outcome in one group in a specific period of time. While the incidence, which we can call it risk, cumulative incidence, absolute risk, these all mean the same thing. And this is again the number of people with a new outcome among a group during a observation period of time, not a specific point of time. It does not count for any outcomes at baseline, and it does not count for variables time of observation. And we use that in cohort studies. You have the incidence rate, which we also call the hazard rate. And this is again the same as the incidence or the risk or the cumulative incidence or absolute risk, so the point just above, but it does not count outcomes at baseline, but it takes time into consideration of how much you actually followed the patient. Let me make, obviously this probably made no sense what I just did now. Let's try to give it a bit more sense through this table. So if you look at this table, we have 10 patients. We followed up these patients for different times, for different reasons. First patient for 3 years, second patient for 5 years, 4 years. And we're looking for the occurrence of metastasis in this group. These are cancer patients, and we're looking at the metastasis occurrence. And we have two columns here. One is saying, did the patient have metastasis at baseline? So 0 is a no, 1 is a yes. And the second one is asking if, so before we started following the patient, so they came already, they have metastasis, or if the patient has metastasis during follow-up. And that means that there are new incidents of metastasis that happen during follow-up. So if we want to look at the prevalence of metastasis in this whole cohort of 10 people, I want to look at the time element. I just have this period or a specific period, and I just need to know how many metastases I see in that whole period. 1, 2, 3, 4, 5, 6 in 10 patients. So 6 out of 10 had metastasis, 60%. I don't care when, was it new, was it old? I'm just looking now at this period, and I have 6 people that have metastasis. If we want to look at odds of metastasis, it's close to the prevalence, but here we're just not looking at 6 out of 10, not looking at the positives overall. We're just looking at the positive over those who didn't. So 6 out of 4. So we can say the odds is 1.5. So we have 6 had metastasis, 4 have no metastasis. Again, no relationship to time. It's just now across this period, which could be a point in time or like 10 years. But we don't care about whether they were there to begin with or they develop now in this period of observation. So the odds is 6 over 4. 6 had metastasis, 4 didn't, so 6 over 4, this is 1.5. Now the incidence, which we also call risk of metastasis over 5 years, because that's the longest that you have a follow-up, is 4 over 8. Why? Because we said when we look at incidence, we don't count for anything that already was there before patient went into the observation period. So those patients 4 and 5, they already had metastasis. We will not be counting them. They're out. They're not at risk here. They already had the metastasis. So I will only count those 8, and I find that 4 of them had metastasis during the 5-year follow-up. So the incidence is actually 4 out of 8, 50%. Now the incidence rate, which was also called the hazard rate, and this is the most complicated one of them, it's the same as the incidence. So it's 4 in terms of how many. So we don't count what happened at baseline. We only count what happened during the observation. So 4 occurrences of metastasis, but we don't divide only on 8 on the number of patients that were at risk, obviously excluding these patients 4 and 5 because they already had it. We also tag a number for how much we actually followed these patients for. So if you look here, the first patient was followed for 3 years. But why do we have, so we put 1 times 2.5. Why do we say 2.5? Because we don't know when during this year they got the metastasis, because the time they got the metastasis, you got your outcome. The follow-up stopped. But we don't know if this happened in the beginning of the 3rd year or at the end of it. We consider it happened at the center of it. So we say this patient was followed until the outcome, 2.5. The second one, for example, was followed again for 5 years. So 1 times 4.5. So we consider they were followed for 4.5 years until the metastasis occurred. These 2 patients that are left were followed for 4 years. So it's 2 times 3.5. And then I had 4 patients, the ones with the 0 here, these 4, were followed for the full 5 years. So 4 times 5. They didn't have an occurrence, so we don't need to make it 4.5. When you do the math, this is what it gives you, this value of 11 per 100, which this is usually the way we describe it is saying this is 11 per 100 person per year. These will make much more sense in the next session. I just wanted you to be aware of them. And from all of these measures, we get the ratios. All of these measures have a ratio, and this is the one that you're probably most commonly accustomed with. One thing to tell you is that I'm giving you the most exact, sharpest way to label these variables or these metrics, sorry. But in the literature, you're going to find them in a very messy way. So odds ratios can be called relative risk, and relative risk called hazard ratio. So it's fine as long as you understand what you're looking at. But if you want to be exact, this is the best way to describe them. So when we talk about ratios, it means, okay, I got the odds of something in group A, and then I got the odds of the same thing in group B. Odds ratio is this over that, as simple as this is. So if we said that, for example, for the prevalence, so group A, which is patients coming from Spain into the UAE, 20% of them had COVID on entry to the airport. This is the prevalence of COVID in passengers coming from Spain. You take the passengers coming from Italy, you find a prevalence of COVID of 30% when you test on arrival. So you have 20% over 30%. That's a 2 to 3. That's what we call the prevalence rate ratio. The same thing for odds. So if we calculate the odds, if there were 100 passengers that came from Spain, 20 of them had COVID, so the odds are 20 over 80, so 2 over 8, so 1 over 4, so 0.25, and then some other ratio in the group coming from Italy. So this is the odds here, the odds here. The odds ratio is this over that. Same thing for incidence ratio, or what we call, we have the incidence, so incidence ratio. We have the odds ratio. We have the incidence rate. It gives you the incidence rate ratio or hazard ratio. Again, you will have these slides. You can go over these terminologies to get more and more used to them. The one thing that is common for all is that when you want to interpret these, when you want to describe them in the DAX, how would you describe it? If someone told you the odds ratio is 2.5 in group A versus group B, this is how it will be reported, because we said there is an odds of something in group A, the odds of something in group B, and then the odds ratio is this over that. So this is how we say that group A are at, let's say the odds ratio is 2.5 for metastasis, looking at that example. We say that group A are at 2.5 times increased odds, or obviously risk or hazard, whatever you use from these ratios in this table, of metastasis than group B. 2.5 times increased odds, increased risk if we're talking about incidence, increased hazard if we're talking about incidence rate of metastasis than group B. And in reality, this means 150% times increased odds, because when we say 2.5 ratio, the odds, because their odds is 1, and then 1.5 more than that is 150% times. But obviously, when it's lower, and it's something, when we say 0.5, again, this is a ratio. When something is a 0.5, we say group A are at 2 times decreased odds of metastasis than group A. We just divide 1 over the 0.5 to reverse it, and we reverse the increase versus decrease. So either group A is at 2.5 times increased odds of metastasis, because the odds ratio is 2.5, but if the odds ratio is 0.5, which we call protective, it means it's at 50% lower chance of odds, or 2 times decreased odds. It's 1 over 0.5. These will only become easier when you get them in practice. Probably you will get those numbers already from the statistician. So all you need to do is go back to a guide like this to see how to actually describe them. I'm not going to go much into multivariate and regression, simply because it takes a lot of time to explain it, and I will go into this later on in the next session next Wednesday, when we talk about confounding and adjustment. But this is when you start looking into the effect of a third variable on the two of interest. So if we're looking at age and hemoglobin level, how does smoking play a part in that? That would be your question. I will talk about this triad of linkage later on, but just to know that when we talk about odds ratio, when we have odds ratio, a case control study, if you look back at all the previous slides, we said odds ratios. If you want to, if you're using odds ratios, then your multivariate regression model of choice is a logistic one. If you're looking at hazard ratios, it's a Cox regression model. That's the main distinction that you need to know of now. How does that work? It's just mainly trying to give an odds ratio of different variables for a common outcome. Again, I prefer to explain this to you in the next session, when it goes into why do we actually do these regressions, to be able to understand adjustment for certain variables for their effect on something else. Linear regression, so one thing I failed to mention is the logistic and Cox regressions are what we use when the outcome of interest is binary. It's something that is categorical. So it could be a heart attack, yes, no, sepsis, yes, no, metastasis, yes, no. That's when we use logistic or Cox regression. But the difference is if we're dealing with odds ratios or hazard ratio, there is a time element or there is no time element. When we look at linear regression per se, that's when the actual outcome or the actual dependent variable is a linear variable. So it's blood pressure. Blood pressure is a linear variable. So I want to look at the effect of age on blood pressure, but also to adjust for certain things. That's why we have a multivariate. We have many things in one mix in one model, and we will talk about these in the next session. What the linear regression mimics is what we spoke of before, the correlation, the Pearson and the Spearman, but this is more or less giving you the linearity even of that relationship. Not only because when you do a Pearson or a Spearman correlation, it gives you the R and it gives you the p-value. So it can tell you if the correlation is strong or in what direction, positive, negative. But what you're mainly getting is knowing that if this goes up, the other goes up, or this goes up, the other goes down. Here, it tells you exactly by how much actually the relationship is being, the correlation is. So if I go 5 years of age, then the hemoglobin level will decrease by 2, for example. So that you can get from a linear regression that gives you an equation, and we will talk about that later. One key peculiar test that I use a lot in my analysis is the receiver operating characteristic curve. This is where all those values of sensitivity and specificity come from. They're always confusing to think of. It's always better to go to a source, find this table that tells you false positive, false negative, and try to understand what is sensitivity, what is specificity. But in general, for your purposes, we said that the univariate test, the dispersion, means, medians, etc., we use them to describe our data so that we can tell the audience about our group of patients without making any correlations. The same for prevalence, incidence on their own. And then we use bivariate studies to compare different variables to each other. Whether they're continuous and categorical, we have different ways. And then we said the multivariate is when we're comparing two, but we still want to see the effect of a third. That's when we do this. So these are the main basic analysis that you would do, especially in observational studies, but even in clinical trials. This receiver operating characteristic is more for prediction. If you want to know the relationship between a variable and an outcome, an exposure and an outcome, in terms of prediction, can it predict it? This is where you do this test, and it gives you few things. It gives you a value of the sensitivity and specificity on a line chart like the one you see here, and it tells you for each data point in your database how much it can predict the outcome. So if we have, let's say, blood pressure again, and the outcome is death. So you put these in the equation, you put these in the statistical software, and it gives you a list of sensitivity and specificity for each blood pressure value, how much it can predict the myocardial infarction or death, for example, in 20 years. So that you would be able to know, can I use these threshold? Which threshold should I use to be able to predict the occurrence of myocardial infarction to the highest sensitivity or specificity? Obviously, the best use of this whole analysis is to actually look at diagnostic tests, because that's why we do them, to predict a future outcome. But we many times use this in the data to see the behavior of a certain variable. Can it predict something for me in the future? One thing that you get always asked in the paper to point out is the value, the threshold, the magic threshold that can predict something. And there isn't actually a clear answer to that, because sometimes you're interested in a value that gives you 100% specificity, but you don't care what's the sensitivity. And specificity and sensitivity, as you see here, they're measures of how accurate, let's say, it can tell you that something will happen or will not happen. Let's keep it as simple as that. So when I'm asked to say, what is this best threshold of my variable, it's sometimes hard to identify. It depends on what do you need from it. But if we want the best of the best, I usually go with a simple formula. I look at the sensitivity and specificity of all of my variables in the database, all the spectrum of variables for a certain values for a certain variable, and I take the one that has the highest sum of sensitivity and specificity, as if they need to both be good. So if I have one that has 80 and 70, I prefer it over 60 and 40, for example, for sensitivity and specificity. And usually, actually, this is the point that is actually in the corner of this famous sensitivity and specificity graph. In this specificity sensitivity graph, there is something also we commonly call the area under the curve. What you would need to know for that is that this is, again, like we spoke about the R in the correlation, the same, there is a p-value to tell you if it's significant or not, but more important than that is the value of this AUC itself. If it's somewhere, it has to be somewhere between 0 and 1. If it's more than 0.7, this is commonly represents that this was a good model. I can rely on this good model to predict myocardial infarction based on blood pressure. The next thing to go over is the survival. Survival curves are obviously something very common in oncology specifically, but obviously across disciplines. Let's assume this example of a group of 7 patients, again, that were started to be observed at different time points, different years. And they were observed for different periods, for different months. So this patient, J, for example, we started observing them from the year 2001 for 27 months. And the last known status in this for this patient at the end of these 27 months was that they were dead. This patient G, we followed them for 28 months and they were alive. So you see, all patients we started observing all patients at different time points for different durations, and they had different outcomes. If you put this graphically on a graph, you will see that these patients, it's a bit messy to interpret this because you can't understand what's happening. If you look at the calendar time at the bottom, so this is 1/1/2000, then year 2002, 2004, 6, 2008, and then each patient we started knowing something about them at different points in time. They were observed for different lengths and had different statuses. What we do actually in survival analysis is that the software and the actual, survival analysis itself, which is the construct of what we call a live table, almost average all of that in a way so that you can actually better interpret. So what these points of patients reaching the end of observation and being alive still, we call it withdrawn alive. I will refer to it. But what the actual survival analysis is doing is taking everything backwards, as if everyone started at the same time 0, and then we're following up per years or months, not on a calendar year where everyone started differently. And that is what will allow us to compare survival between these patients, of how long they were followed and how long they lasted in a study. I'm not going to go in detail in this, but the survival curve that you see usually come from what we call a live table. I'll just go over one row to tell you how things work. So usually what we do is we split the time period of observation in a trial, whether it's a 1-year or a 10-year trial, and look at windows of timing. So if we assume here that these represent years, the column T, and we have the first time window is from time 0 to time 1 year, from 1 year to 2 years. And then N is your number of patients that entered the study alive, obviously. And we consider them all at risk. They all can die within this trial. We're looking at the outcome of death. So we start with these 50, entered the trial at time 0, and we're describing here in this row what happens to them in the first year. So 9 of them died. We know that in this period. 0 of them left the trial. No one withdrew from the trial. They all stayed on put. And then this N with an apostrophe is what we call the adjusted number of patients at risk. And this is usually the N, which is the 50, minus how many withdrew, actually. So we have 50 that are actually at risk in this period of 0 to 1. And the PD, which is the probability of death during this time period, we just take how many died to how many are truly at risk. So 9 over 50, that gives you 0.180. Then how many probability of surviving is simply 1 minus this one, so 1.80, 0.820. And the cumulative probability of survival, it always starts with 100. Now let's see what happened in the second year. So in the second year, we have starting from year 1 to the end of it, so to year 2, Now we have 41 patients that entered this time period because 9 of them died already. 6 died in this time period. 1 of them withdrew. So if we want to look at the adjusted number at risk in this period, we said we take how many entered and we subtract the one that actually withdrew. We cannot consider them at risk. But similar to how we did a bit earlier, we don't know when this patient left the study. Did they leave at the beginning of the year, at the end of the year? So we only subtract 0.5. We consider as if we had half the year this patient was exposed and was at risk. So we consider him as if half a person in reality. So the number at risk is 4.5. So your probability of death is simply 6 over 4.5. That gives you 0.148. Then the probability of survival is 0.8521 minus 0.148. The cumulative probability of survival, you simply multiply the 0.82 by the one number that is above it. So you always go with the year that is before multiplied by the year that is preceding. So this 0.699 will be this times that. And all of this is something you will never do manually unless you have a very small trial that you're doing it. The important thing is to know how to actually look at this table and what does this number mean. This is the number that we care about the most, the last one, the cumulative probability of survival. And this is where what you see on the survival curve. It starts with 100 and then it starts going down. It's the cumulative probability of survival. So if I want to know what is a 5-year survival in this life table, I will just simply look at the period that starts with a 5 and I just take this number. So the 5-year survival is 56.7% or 0.567. So when you look at the cumulative survival curve, so the specific year survival is you simply go to that year and you look at the ratio in the life table, or you can do it in the graph. You actually look at the year, which is year 5 here, and you go up and you see what is the percentage here. So this line is giving you these numbers, the cumulative probability of survival. Something else you probably hear of is the median survival, although the name is a little bit tricky. But what we mean is this is the time corresponding to 50% cumulative survival. So we go down our graph, we see where do we reach 50% cumulative survival. This is 0 to 100, for example. This is the 50% line, and then we simply go down and see on the time scale how long was that. So maybe it was at 6 months. So the median survival time is 6 months. That means by 6 months, I lost half of my population. When we need to compare two survival curves, if we're comparing two groups, two risk factors, two interventions, we use usually what we call the log rank test to compare these survival curves, and it gives you a p-value. If the p-value is significant, it means these survival curves are well separated from each other, and that's where we say that the treatment of the group that is, showing better survival is significantly more effective or has a significantly better survival than the other one. There are many types of survival that we look at. These are just example of 3. We look at overall survival, which means the outcome that we're interested in, like we just did in the table, is death. Progression-free survival is mortality or disease progression. So the disease advance, we're talking oncology mostly here, but obviously the progression of disease is also coined in many other indications and diseases. And there is also modified progression-free survival, which is mortality or disease progression or not complete remission in oncology at least. So there are many different ways, but all that will be different is what you're inputting here in this column of D, death. So this is what I wanted to cover in this hour. I wanted to keep this session a little bit more longer just to be able to take as many questions as we can. I'm sure the topic of statistics is always complicated. You would probably have tons of questions. I'll try to see how many are posted and answer those. But definitely, as I said, you will have those slides available on the IOS website so that you can go and refer to certain tests. Just as a sense check, if you look at something, you want to make sure you're actually looking at the right test. And we will, as I mentioned last time, we will also provide some resources of further readings of you need to. Just to remind you of what's going to happen before I take the questions next time, we will be looking at interpretation of data. So all of these results, we'll see examples of a paper and see how do we interpret the results. And I will go all over all these concepts of bias, confounding, the things that we use regression analysis for, and so on, so that these become more clear. And then the last session will be a joint session about how to actually write papers, how to select the journal, maximize your chances, and how to write papers. Now let me try to see if we had questions. Okay. Micheline, if I don't know if there are no questions or are just they're not popping on my screen. Just 1 second to figure out. Just 1 second. Now they're starting to show. Sorry for that. Yeah, there's a question about if the recording will be available for future reference. Yes, definitely. We'll see what's best for you, the recording or to actually have the slides. Probably the recording is more useful so that you can at least see me speaking to that. And then probably we can have both available with some resources that we can, at least links to resources that you can also rely on. We're going to have that ready by the end of the month because we're going to need to just edit the videos and so on. So after we finish the last session on 30th of March, hopefully it will be immediately available on the website. Okay. Yeah, we have another question with relation to the use of odds ratio versus relative risk. As I said, this is just a choice of terminology. If you want to have like a rule about that, you probably would want to use odds ratios when you're doing case control studies and relative risk when you're doing cohort studies. But in reality, if you just use the word risk in any description in the results, that should be completely fine. There is absolutely no issue with the terminology. In terms of correlation and association, another question. This would be more or less if you use the Pearson and Spearman correlation, as we call them. So if you're comparing two continuous variables, that's where we use the word correlation. While if there is you're looking at categorical and continuous variables, so we're looking at an odds ratio, we found that it's significant, then we would say associated. So I would say height is correlated with weight, but gender is associated with the higher blood pressure, for example. That's the difference of using correlation and association. Okay. Someone is asking about the website where they will be available. It should be the EOS website. Just Google American College Society and they will be available there. There's a question about what we do with missing values. So this is a whole lecture on its own. There are many ways to do that. But the most simple way is, obviously, if you have a lot of missing values in your data, you need to question if you actually can be able to use this data, because sometimes you might just be missing a very considerable proportion of the population that your data will be biased from it. But if it's missing, obviously, value, you have a population, you have the missing values, which is obviously always normal because you can't expect all the data to be recorded. There are various ways to do that. Statisticians usually deal with that mostly in different ways. One common one that is the most simple that I use sometimes, for example, in some analysis, especially if the missing values aren't many, is you can replace the missing values with the mean of the population, so that you can still include all patients. You wouldn't lose them, especially when you do multivariate analysis that affects your analysis. But I would replace their nothing with the mean or median. It depends on if I'm using means or medians. Also, sometimes if it's a categorical variable that is missing, I try to do what we call sensitivity analysis. So I perform the whole analysis. So if I have gender missing for 20 patients, I perform the whole analysis with considering those 20 as males, and then do the same analysis again, considering all those 20 as females, to see the extremes of the findings and say, obviously, if my findings are still, the findings without those anyways are still in between those two, then it's fine. I don't expect any bias, because at maximum it could be this, at minimum it could be that. It depends on how those missing values are in real life. Another question on, how we compare and correlate COVID data statistics for last 2 years with all other viral infection of Spanish flu century before, and how we get evidence, experience, and learn positive findings and pros and cons. That's a good question. So sometimes when you need to do grouping or comparative analysis, and you don't have that available, there were many things that we wanted to know how they were before COVID, but no one cared about them, no one looked at them. And now we only have how it is in COVID. So if you look at anything, rate of stress due to something before COVID and after COVID, you don't find the data before COVID. That's an issue, obviously. But if you find it and you don't have it at the time of COVID, you can always do comparison with historic data. Obviously, the ideal way to do this is to do a collaborative study with someone and actually find the raw data and include it as if you just collected it. But if you need to compare things with the data that's available in the literature, it's sometimes tricky. I'll talk about this a bit in the next session. But for example, one thing I use usually that gives me a little bit of sense of comparison is to rely on confidence intervals. So if I found in my population a certain finding, a certain mean of 5 with a confidence interval of 6 to 8, and I don't have anything in my own data to compare it to, but I have something historically, if I have that mean value of, something that happened 100 years ago with confidence interval, I can at least say those confidence intervals don't cross, so they are significantly different from each other. But I need to explain to you what confidence intervals are before you understand that, so we can do that in the next session. But you can always rely on some of these, let's say, advanced reporting measures with your data, so you can compare data from different sources. If you want to do it officially, obviously we always say we need to do a meta-analysis, get the raw data, compare it in different way. But I'm talking about a very simple way to just pick a number from the literature and deal with that. Okay, I think that was it in terms of questions. Obviously, as I mentioned earlier, can be more than happy to connect with everyone here. On LinkedIn, you can find me, and if you have any questions ever, please feel free to ask me, and I'll point, even if I don't answer, to the right resource. Hopefully, things will still be on track and time. We don't expect any changes, but if so, we will inform you. And anyways, we will advertise the next session before it happens. So that will be Wednesday, 23rd March at 8 p.m. Dubai time. Hopefully, we'll see you all next time. And thank you for those that joined today. And hopefully that we will see each other next week. Thank you.